Okay, so in this last video, we are going to, I think this is the hard bit of linear programming,
Me too.
and I think this is where I might get stuck. So it's basically having a load of words and turning it into the inequalities that you can then turn into the feasible region that you can then do the stuff on. So let's have a look what structure we're going for. So this is the formulation of a linear programming problem. Looks like this, got 3 sections. Obviously we need an objective. I've been usually using red for an objective, and the objective is we are going to maximise or minimise, and you'd be amazed how many students forget to say this. You know, it's kind of the point really, isn't it?
Yeah.
Maximise or minimise, and then whatever it is, it might be something like that, you know. But that's your objective. You want to maximise or minimise a particular function.
So it's good to write that down.
Yes, it's part of the construction of the problem, because otherwise, if you were in an exam and it had a feasible region and then it said solve this linear programming problem, but it didn't tell you whether to maximise or minimise, then you don't know which corner you're going for, so you can't do it. So unless you're stating whether you want to maximise or minimise and what the function is, you're not setting up the problem in a way that it can be solved. The constraints are the things we were working on in the last video, the inequalities. So maybe x has to be bigger than or equal to 10, y has to be 0, even 10, and y has to be less than or equal to 50, and maybe 2x and 3y has got to be less than or equal to 15 or something like that. You know, whatever these things are, yeah. And no, I'm not going with ones today, just going with the second digit. So those are our sort of constraints that we're usually doing. Now the bit that students forget is what currently isn't on the board. It's obvious there's constraints. It's fairly obvious that you have to have an objective. Sometimes the mark scheme specifically asks for it anyway, so it highlights the need for it. What students forget is to state what x and y are in a way that makes sense. So what are x and y? Now what you can't do, which is what students do, is say, oh, what might we be making? We might be selling apples and bananas. And then we'd use A and B. We might be, what cars we were doing? We were doing how many
Types of cars.
Types of cars to buy.
Yeah.
Okay, so this might be like type A car, and Y represents type B car. Now that is nonsense, because it says x equals type A car. And does it seem obvious to you why that is wrong?
It's too variable. Why aren't we just calling it A?
Yeah, you would just say A really, wouldn't you? A equals A. If you want to refer to the type A, then you would just say A. Exactly. What we're doing when we're talking about x, and the x that's down here, and the x that's in all of these constraints, x is the number of, and it seems like such a stupid little extra thing, but it's really important. It makes it into a number. The variable is the number. So you must have x equals number of, y equals number of, and then whatever it is, baskets, bananas, type B car, whatever it is.
Of course, because you're talking about objects, aren't you? You're talking about a sum of those objects.
Yeah.
When you're making the number of cars.
Yeah, you're specifically defining, you're making up these 2 letters x and y, and then representing something, and what they're representing is the number of. So when we come down to the bottom and we say what's the objective, it's to maximise or minimise this. So basically you're saying, what is
the number of?
Yeah, what is the number of those that I should buy, and what is the number of those that I should buy? So number of, really important. Now, the other thing within our constraints is that we can't have negative cars.
So those have always got to be included.
Pretty much, yeah. I mean, if it was an abstract problem, then you could have negative x and y, but if it's anything to do with reality, and, well, actually, no, because you're trying to make the number of, I've just said that to myself, the number of these and the number of these, I can't think of any situation in which the number of things would be negative. That doesn't really make sense, given that we are dealing with an actual problem. So we can't have negative x and y, and that's a constraint that students often forget to add. And the other thing is, not always but sometimes true, and we have this with the cars, x and y must be whole numbers. You can write it like that, or you can say x and y must be whole numbers. That's what that says, x and y must be whole numbers. So you can either write it like that or write literally the words must be whole numbers. So this is what we're doing. What are the decision variables? What are the constraints? What's the objective? That formulates the problem. Let's have a go. Okay. So what are our decision variables? Shall we use x and y?
Yeah.
Okay.
So x is the number of trucks.
Trucks. Okay. X is the number of trucks.
Y is the number of bicycles.
Y is the number of bicycles. Okay, that's the beginning now set up. We've defined our decision variables. It says already that we need to maximise profit, but have we got a formula for profit? What do we want to maximise? Maximise, what would the formula be?
So each bike gives a profit of 15,
Okay,
and each truck a profit of 11. So you'd have 15y plus 11x.
15y plus 11x. That would be the profit that we'd make depending on the number of bikes and the number of trucks.
Yeah.
Okay, where x is the number of trucks and y is the number of bikes. Okay, so that's kind of the beginning and end. We've got the decision variables defined and we've got our objective. So what about the constraints? Any obvious constraints?
Well, the ones that we often forget.
Yes, the ones we often forget. So let's get those straight away. X and Y, you can't have negative bikes or negative trucks.
Nope.
And you can't have half a bike or half a truck. Have to be whole
So you
numbers.
try,
Yes, exactly. Okay, so they're the obvious ones. Now the less obvious ones.
Well, we've got a table.
Yep.
Helpful.
So the bike is taking
1 hour in the morning.
5 hours to
Yeah.
make.
Yeah.
An hour in that, 3 hours in that, 1 hour in that.
Truck just 2 hours.
Truck. So the moulder is only needed for the bike. So for each bike, we need 1 hour in the moulder. So if we make Y bikes, we would need Y hours in the moulder. It says here that we can only operate it for 3 hours per day.
So that means we can only make 3 bucks.
Yes.
So,
So-
we've got constraint.
so
Y
the-
equals 3.
So the number of bikes must be less than or equal to 3?
Yeah.
Yeah. Okay. What about the next thing? The lathe can only be used for 12 hours.
Okay, so for every bike, you're using 3 hours.
Bike, 3 hours.
And for every truck, you're using 1 hour. And that's got to be less than 12 hours.
Or
less than or equal to 12 hours.
Yeah. Okay, I agree with that. Yep. So the number of bikes times 3
Yep.
add the number of trucks is the total amount of time you'd need the lathe for, and you've only got 12 hours. Yep.
Yep.
And the next one?
So it would be 1 hour of bikes and 1 hour of trucks. And it has to be less than or equal to 7.
Yep, I agree with that. So these are the things that we would draw on. First of all as lines, and these.
Yeah.
Yep, so we draw the lines on first of all as lines with y equals 3, 3y at x equals 12. Then we'd work out which side to shade away. That would reveal the region. Then we could plot the line, move the ruler, or do the vertex method. Solve. Done. Good. Let's see if they get any harder.
Maximising sales.
Maximising sales. So maximise P equals, where's the profit? Here we go.
So, well, should we set up our decision?
I think we need to set them up, don't we? I'll squash them at the top. X is the number of
chair A.
chair A, and Y is the number of
Chair B.
chair B. Okay, so they're set up. So our objective is to maximise the profit, and we get £10 for every chair A, so that's 10x, and we get
12.
£12 for every chair B. So that's 12y. Okay, good, right. Obvious, obvious constraints. We can't have negative chairs, and we can't make half a chair. Okay. Wow.
It's a lot of writing, isn't it?
Yes, huge amount of writing.
Can we make a table?
The table was helpful, wasn't it?
It was.
Okay, let's make a table. So,
Chair
what
A,
have we
chair
got?
B, anyway.
We've got chair A and chair B. Yeah. Yeah.
And we've got department 1 and department 2.
Okay. Department 1 and department 2. Okay.
Right. So chair A is processed in department 1 for 3 hours,
3.
and then in department 2 for 2 hours.
2.
B is processed in department 1 for 3 hours, and in department 2 for 4 hours.
Okay.
Right. So time available in department 1 each month is 120 hours.
So, if we make X chair A's,
Yeah.
then department 1 is going to have 3X hours needed for all the chair A's,
Yep.
and also 3Y hours needed for all the chair B's, and that
Less than two.
can't, yeah,
Yeah, so it can't go over that.
yeah. And then in department 2, so for every chair A we make, that's going to take 2 hours. And for every chair B we make, that's going to take 4 hours. And that can't exceed 150 hours.
Yeah.
I think we're done.
I think so.
Excellent. So the table's really helpful. The table sort of made it really clear, like in the last one. The table's a good plan. Okay, last one. Hopefully. Let's see how we go on with this one.
Hello, Karen.
Karen's going jogging and cycling. Well done, Karen. She jogs very fast, 6 miles an hour. Well done, Karen. And she cycles. I don't know if that's fast cycling because I've never done cycling. And she,
Gains of robot points.
so an hour. Should we set up our decision variables?
Yes.
Okay. So X is, Y is number of. Is it hours doing something? What does she get points for? An hour of jogging.
Yes.
So it must be the number of hours. So number of hours jogging. And Y is the number of hours cycling. Okay. No, is that wrong?
Well, each week she'd like to earn at least 12 aerobic points. It looks like it's sounding like our profit line, but not profit line. That one.
Yeah.
Cover at least 54 miles.
Oh yeah.
So should we be working... Although actually, that's all right, isn't it? Miles per hour.
Yeah. Okay. I think this is going to be really complicated. But I think the hours thing is okay.
Yeah. Okay.
You're right. We might have to come back to that. But at the moment, if we work with X's hours and Y's number of hours and then just see if it goes wrong.
Okay.
Okay. Can we, what does she want to actually do? Minimise the total amount of time spent exercising. So she wants to minimise P equals X add Y.
Yeah.
Because X is her hours jogging, Y is her hours cycling, X add Y total hours exercising, minimise it.
Mm-hmm.
Okay, so that makes sense. So obvious constraints, X and Y have to be positive. Yeah, you can't have negative hours, but they don't have to be whole numbers.
No.
Because you could do 2.5 hours of jogging easily. Well, not easily, you'd get tired, but you could do it. So that's the only obvious constraint.
Yeah.
Okay, other constraints. Okay,
Okay, so each week she likes to earn at least 12 aerobic points.
okay. So she wants to get at least, so the number of points is bigger than 12.
Bigger than 12.
Okay,
So 1 hour of jogging gains her 4 aerobic points.
so 4x.
Yes. And 1 hour of cycling gains 3. So it's 3 Ys.
Okay,
She wants that to be greater than 12.
Yep, that makes sense, yeah.
And then,
Oh my goodness.
so she wants to cover at least 54 miles.
Okay.
But she can do that either by walking, by jogging or cycling.
Okay, so at least 54 miles.
Why are we doing the miles?
Okay, so if she does an hour's jogging, how far... No, this is obvious, isn't it? If she does an hour's jogging at 6 miles per hour, then she's gone 6 miles.
Yeah.
Okay, so
So
6x
X.
is how many miles she's gone.
Yeah.
And 18
Yeah.
y. So that's the number of miles she's gone, and that has to be within
Yeah.
54. Okay. Okay.
Yeah.
And what's this last bit?
Oh, and cycle for at least twice as long as she jogs.
So cycle for at least twice as long as she jogs, or cycles for at least twice as long as she jogs, or cycles for at least twice as long as she jogs, or maybe it's cycles. Okay, something to do with an x, a y, and a 2.
Yeah.
Okay.
And an inequality.
And an inequality, yes. Okay. Right. Okay, this is hard. Let's go on to another page for this. Okay. This is the hardest thing in linear programming, I think. It makes my brain explode. At least twice as many x as y. So it's going to have an x and a y and a 2. But what happens with the x and the y and the 2? Usually if I ask the class to vote on this, it's like 25% for each one.
Yeah.
Because it is really confusing.
Yeah.
So, we can think of it using examples. At least twice as many x as y. Can you give me an example of an x and a y where I have at least, or like more than, twice as many x as y?
So if you had, say, 5x and 2y.
Okay, so I would be saying, how many y have I got? 2. I need to have at least twice as many x's than that. Yeah?
Yeah.
So notice that it's the 2 that's the focus here, because you chose y as 2.
Yeah.
So because y is 2, should we? Yeah, we'll use 2, even though there's 2's everywhere now. So because you chose x is 5 and y is 2, but the point is you chose y as 2, okay? So this is what needs to be doubled, isn't it?
Yeah.
And then we make a comparison here.
Yeah.
So we're starting by looking at the y, we're doubling it, and then we're comparing the x. So we can already say that these are wrong,
Yes.
because it's the y that's being doubled. And this may not be a very good mathematical way of remembering it, but I remember it like this. Whichever one says as, that's the one that gets doubled. Or tripled, or quadrupled, or whatever it is. In this case, doubled because it's twice as many.
Yeah.
But it's as y. You're taking the y, you're doing something to the y, in this case doubling, and then you're comparing your x to see whether or not it is that thing. So that's the first thing. So we get our y, 2, we double it, 4.
Mm-hmm.
Now, do we want that x value to be bigger than 4 or smaller than 4?
We want x bigger.
Bigger, because it says at least, at least. So you take your y, you double it,
Yeah.
and then that kind of forms a lower bound for what x could be. X can be at least that, but it has to be at least it. So x could be anything up here, anything bigger than the 2y, but certainly not smaller. So it's at least twice as many. So we need the x to exceed the 2y. So this is the one we're looking for. X is bigger than 2y. If we go back to this one and have a look at the way this was phrased. Okay. She needs to cycle for at least twice as long as she jogs. As she jogs. The jogging is the focus here. We take the jogging as the focus. We double it.
Yeah.
We're going to compare the cycling to that. She's got to cycle at least twice as much. Could be more,
Mm-hmm.
but at the very least twice as much. So that's the way around it goes. Y is bigger than or equal to 2x, which is kind of the hardest thing,
It
really.
is the hardest thing.
Yeah. So that's it. I think we've covered. Obviously, this is a difficult part of linear programming, but you get the general idea. Set up your decision variables. Get all your constraints in, including the obvious ones. Think carefully about this. Twice as many, at least at most, that sort of thing. And then set your objective to minimise or maximise whatever the function is.
Mm.